I do have to leak into it sometimes, so if you can't see it, feel free to move around and that sort of thing. Okay, let's jump into it. So today we're talking about intro to graph theory. We're good? The chapter, for whatever reason, is called Decompositions of Graphs. So really, first let's think about why we want to use graphs in the first place. So what makes them useful? So if we're trying to, for example, go all around South America, we can be using a traditional map, but it has all, if all we're trying to do is figure out what countries are adjacent to one another, it becomes less useful. So you have all this additional information, all these fancy boundaries, and suddenly you're trying to, if you just ask what countries border Colombia, it's a harder question to answer. So a graph is supposed to be a really simplified version of other sorts of data that you could then manipulate and look at the properties of and hopefully come away with meaningful, useful information. So what a graph is, all it is simply is a set of vertices, also called nodes, and a set of edges between the different vertices. So like B here being an example, mirroring this map. So for in this map particularly, there's nodes 1 through 13, and then there's a number of edges 1, 2, 7, 13, 6, 8, 8, 6. Like there's in an undirected graph like this, go both ways. But yeah, so that's kind of an example of a graph. So it has actually relatively little to do with like a bar graph or like a scatter plot or whatever.
You can make a really terrible bar graph.
You could. I don't know how useful it would be. Okay, so some properties. So there's going to be, particularly for undirected graphs, there's going to be symmetry of edges. So whenever you have some pair of edges, x and y, so like, for example, an edge between 1 and 2, you also have an edge between 2 and 1. This is kind of a base property of an undirected graph. The edges go both ways. So in terms of notation, undirected edges are going to have these little nice curly brackets, and directed edges are going to have the straight parentheses. So if you were to make a graph of the World Wide Web, what would the vertices and the edges be? So if you're trying to map out the World Wide Web and all these different sites, how would you kind of think about it in the terms of a graph? Anybody have any ideas? That's a good place to start. So what would a link be? So yeah, the links would actually be the edges, and what does that make the nodes or vertices? You have an idea? Can you sit up, please? Like, it's not nap time.
Yeah, IP.
Not necessarily. Let's think about it just websites.
Okay, so websites.
So yeah, so websites, and then like that's going a level deeper. We don't need to do that yet. So if all of the different, so if you think about it, you think of every single website in the World Wide Web as individual nodes, and you think of all the hyperlinks that connect them as the edges, that's a huge, huge graph. But also really interesting, because if we can have some idea of the topology, of the structure of the web, then we could do things like better predict traffic to different websites, and which could lead to certain economic returns. So for sociologists, for economists, for computer scientists, trying to have an idea of this particular object, the World Wide Web, is very interesting. So what's awesome is even though this graph would be huge, monumental in scale, a lot of the properties can be found in linear time. So if there's a couple billion, maybe a trillion nodes in the World Wide Web, trillion websites, we could still get through all of them in a somewhat reasonable time. So there's actually two ways to represent graphs when you think of actual structures and objects. The first is an adjacency matrix. Think about, or look at this graphic down here. The good thing about, oh nice, we got some lights on. The good thing about graphs is that we've got a lot of nice visuals throughout the next couple weeks as we explore them, which makes it easier to understand, I like to think. So basically what you're going to do with an adjacency matrix is you're going to have each of the nodes has both a row and a column. And whenever you find an edge, you place a 1 there. So for example, this is an undirected graph. You can tell that from the picture by there being no arrows. So you're going to see that, for example, to represent this A to B, you have 1s at both AB and BA. Cool? So that's a way to represent all this information in one matrix. So it makes it really simple to check if there is a connection between two nodes, because you just look in the matrix, which is constant time. But the challenge with this particular representation is that the space that it requires to hold all of it is really, really large, because you need each of these spaces is n squared, if n is the number of nodes, because that's how big the matrix has to be to represent all this data. So yeah, and if it wasn't clear, if there is an edge, the space is a 1, and it's a 0 otherwise. So an adjacency list is a lot more like a linked list. So if we think of particularly, so if you started at one of these nodes, say A, it would then have the information, or the memory addresses of B, D, and C, which would then also be another representation. Now this takes a lot less space, but if you're trying to traverse and check and see if an edge exists, it takes a lot longer. And also what I did point out is, if you look at this particular node D, you'll see there's a little curve going to itself. That means that, if you look on here, D is actually also a node that is marked, meaning that it also connects to itself, which can happen. So a little loop right there. So now checking for an edge is not constant time. When the structure is only as large as the number of edges that exist. And it also is really easy to go from one node to another, because you then have this nice property that you can just follow along. So density of a graph. This is actually a pretty complicated question. So when we're thinking about the size of a graph, we have to be both thinking about the number of nodes in the graph, so the number of websites in the internet, and the number of edges in a graph, so the number of links, for example. The number of edges can range from about the number of nodes. If it gets much smaller, suddenly you have all these disjoint nodes sitting off by themselves, so it becomes less interesting at that point, to about all of the nodes, which is the number of vertices squared. We then draw a distinction. If the number of edges is close to the number, to the maximal number of edges, it means that all of the different nodes or many of the different nodes are all connected to one another, and we call that dense, which means that there's a lot of connectivity in that particular graph. If it's at the other end of the spectrum, we call it sparse, meaning that there's not a lot of connections. So as we think about this graph of the internet, would it be more dense or more sparse?
Dense.
So another way to think about this is you have a whole bunch of nodes, websites. Proportional to the amount of websites in the internet, how many is any one node connected to via hyperlinks? Very true.
Are we connecting through advertisements or not?
We can count advertisements, sure.
Is this website Google?
Google would have a lot of connections, yes. But actually, the average amount of hyperlinks, because for every Google, there's 100 Joe Blow's blog where he doesn't have any hyperlinks at all, and they do average out over time, is about 6 hyperlinks. So it's actually monumentally sparse. In fact, if you tried to put the internet into an adjacency matrix, it would be thousands of terabytes worth of memory. Whereas if you put it into an adjacency list, it actually can fit on a 1 or 2 terabyte hard drive. You can carry it around in your pocket. So it does, like, the scale really does matter here. I got it from the book, so you can read the book and you'll get it. So now we're going to talk about depth first search. Anybody any flashbacks to fill it? So if you did some more reading about it, a lot of what you're doing is actually depth first search. And you can think about it as a tree and go down that rabbit hole. For those that I attempted to do so, looking at Dan. So when we're thinking about a graph, we have a couple questions that we can ask when we're thinking about its properties. So for example, which parts of a graph can you get from a given index? If you start at index A, and you just have the memory address of index A, how do you know how much of the graph you can get to overall? So one way to actually think about this is in the form of thinking about a labyrinth and trying to navigate through a labyrinth. Because if you think about it from a computer's perspective, all you have is a little bit of memory. So for A, you're just in a location, and you can go a couple different directions, but you're trying to learn the properties of it. So there's a classic problem of you're placed into a labyrinth. What would you need to bring with you in order to explore it all? And actually know you're exploring it all and not get hopelessly lost and confused. Does that ring a bell with anybody?
You mean Legend of Zelda?
Torches. Yeah, torches.
Skyrim?
Breadcrumbs is a good one. But there's one thing.
Ball of
The
yarn.
Minotaur?
You're thinking about
So,
We got a little sidetracked.
so actually, those are the two that I was looking for: chalk and string. So if you evolve string, then you can follow it, and if you get to a dead end, you can turn back around and go to the last intersection. And then you can mark each intersection that you go by, so you know if you're being led in a loop. So with just a chalk and evolve string, you can get through a labyrinth without any problems. So, what are the computer versions of that? Anybody have any ideas? That would be our ball of string, yes. So that's how we go back and forth, as a lot of you guys have played with. Yep. So when we think about the piece of chalk, all we really need is a Boolean, right? At each of the different nodes, if we do a Boolean, visited or not visited, then we can know if we've gone that direction yet. Yeah. So we're going to define a procedure explore. And it's going to input a graph with vertices and edges, and just one individual vertex, with the little v being within the vertexes. So the capital V is all of the vertexes, capital E is all of the edges, and then little v and little e are going to represent an individual vertex and an individual edge. So kind of the output of this function is you're going to end up going through all of the nodes reachable from whatever v you give it, and go and start exploring them as well. So walking through, first, given some vertex, we want to set that as visited to true, so that we know that if we find it again in some loop, we've already been there, so we don't have to go check it again. And then we're going to define two functions, pre-visit and post-visit. And these are actually, we're not going to define them yet. You can do a whole bunch of different things with them, but the idea is that you can start, you can use these to do work at any given node. So as you enter a node or as you leave a node, and then, so that's kind of what's happening when you're there. And then for each edge that goes from V to U within the edges, if it's not visited, explore. So you should go to the next one and check and see, and then repeat this while you're there. So using explore. So here's an example. If we start at node A, what would happen if we tried to explore this individual graph? So note that K and L are never actually hit because there's no actual connections with them, but everything else is. So you'll start at A, you see B, C, and D. Let's go to B. Then you're going to see E and F. So this is A going to B. E is less than F, so let's go down to E. Then you're going to see I and J. You'll find I, and then J. And then once you get to J, you actually realize that there is one other path to keep going back to E. This is a back edge, and it's going to be basically represented by the little dotted line. And we're not actually going to follow it. So once we hit J, we know that we've gone as far as we can in that direction. Okay, back up. Okay, B, let's go to F now. in this example, we're going to try, or for cases like this, any actual solid edge is going to be a tree edge. And as you can see, for those of you that like trees, binary trees, everybody loves them, right? This is going to form a tree going down. And a tree is basically a graph that doesn't have any loops in it, any cycles. We'll talk more about that a little bit later. So because we're not looking at the back edges, with just the solid edges, this is a tree. And then those are the back edges. Yeah, cool. So now if we want to be exploring all of a graph, we're going to define depth first search, DFS, which is basically going to go through and start counting through all the different vertices. Start with the first one if it's visited. So first, before you do anything, set all of their booleans to false so that you know you have to search this tree, or this graph, rather. And then start exploring the first branch when it has done all of its exploration. So after you've already explored all of this part, it will try to find any other open vertices and start exploring that. So for here, it would jump to K and start looking over there. So does anybody have any ideas of the runtime of DFS? So, huh? ON is a good way of thinking about it. We can be a little more specific. So we're going through at least each vertice we see. And here we're going to be going through at least each edge. So we can think of this as big O of the quantity of V and the quantity of E. So the amount of vertices and the amount of edges, which is going to be ON. So yeah, this is an example of this entire 3.6, this whole graph being broken up and going into a search forest. So when you have a number of trees together, it's thought of as a forest because analogies. So you start at A, and then you explore this whole little piece here, right here. Then you jump to C, explore this whole piece, and then explore F by itself, which is less interesting. Any questions so far about any of this stuff? Making sense? So connectivity. We say that an undirected graph is connected if there is a path between any pair of vertices. So this clearly is not connected. If you're at A, you can't get to F, or G, or L, or whatever, just by following the edges of the graph. But it is made up of 3 disjoint connected regions. So 1, 2, 3. Next. And you could actually write them out. So this would be another form of thinking about this this graph is as these 3 disjoint connections. And we're going to call those connected components. So the connected components of a graph sum up to be all of the different parts of it, with each part being defined as pieces that are connected. So we can adjust our depth first search to actually keep track of which connected component each of these are. So does anybody have any ideas of how we might be going about that? So how would we know based on, jump back there, based on this algorithm here, how would we kind of assign value to each of these different pieces?
What are we assigning?
So we're trying to just number them, basically. So
okay.
let's call this one 1, this one 2, and this one 3. So you want all, so if you look at any node connected to A, they'd all be associated with a value of 1. All of those connected to C would be a value of 2, and F itself would be 3. So now is when we're going to start thinking about our pre-visit and post-visit operations. So for this particular example, as we get to each explore, if we had some global variable, let's call it CC for connected component, that was basically iterating up for each DFS call. So let's say you initialize it in here, set it to 0, and then every time you find a new one that is not visited, you iterate up 1. It might look something like this. So just really simple. In the pre-visit stage, you're going to set it to whatever that CC is, where CC is a global initial that is initialized to 0, and then increment it up. Does that make sense? I can kind of start numbering these trees. So there's another way that we can think about ordering these graphs. And how we're going to be doing this is by basically keeping track of the pre and post visit and just recording those numbers. So for some examples, though it's really hard to see, these little numbers associated with each node. So for example, here at A it's 110. So when you hit the pre-visit of A, when you hit pre-visit, you're going to just take whatever that number is, which starts at 1, and you're going to set that to some variable associated with that. Then you're going to start iterating through the edges. You get to B, you're going to let B be 2. B doesn't have any edges associated with it afterwards. So we immediately set post-visit to 3. Then you go back up to A, and you're still going through its loop. You end up going over to E, so it ends up being 4. And you kind of keep counting up. And what it ends up doing is keeping track of when you get to a particular node and when you stop looking at a particular node. So there's a lot of interesting things that we'll try to do with this. We'll see if we can keep wrapping our mind around it. But one interesting property is that for any two nodes, U and V, they're either going to be disjoint or contained within the other. Meaning, when you hit A the first time, you're not going to end up doing its post visit, so closing it, until you've already gone through all of the rest that are below it. So B is going to exist entirely underneath it with numbers between A's pre-visit and post-visit. And so is E, I, and J. So what this is going to end up being able to do is it's going to end up representing kind of a stack. As you go down, you handle everything, and you come back up. And everything is handled. Cool. So it's last in, first out, if people have heard that term. So we're going to keep playing with this, so if it's a little confusing. Yeah, what's up?
Why do you just ignore the shortcuts and stuff? You know what I mean? Like, how do you go from J to E, for example, G to C?
So why don't we?
For example, like on the post visit, like, you know what I mean? That could be way shorter if you didn't traverse up the tree the other way, like G to C.
So yes, but what we want to keep doing is kind of thinking about this as a tree. So when we find those back edges, we're going to continue to ignore them because the goal is not necessarily to minimize these values. The goal is kind of to just be observing something about this tree that we're later going to use to actually learn more about it. Does that make sense? Okay. We'll keep playing with it so that we can continue to wrap our minds around it. So now we're going to be looking at depth first search in directed graphs as opposed to undirected. So you can tell it's directed now because it has a bunch of arrows. So it's going one way or the other, or potentially both. So there's a whole hierarchy of vocabulary associated with directed graphs. So for this particular node, we consider A the root of the search tree, because that's kind of where it starts. And that's mostly because we choose to start at A. But everything else is its descendant, because from A you can get to any other node, where that's not true for other nodes. We consider E to be an ancestor of F, G, and H, because those all, if you follow them backwards, go back to E. C is a parent of D. D is the child of C. So kind of this family analogy pushes forward in a lot of different ways. So once again, we consider the tree edges, as we were talking about earlier, to be when we decompose this into a tree, the edges that we're following. Forward edges are similar, except for they go from, for example, from A here over to D. We consider this a forward edge because maybe we're skipping a couple nodes, but if you start at A, you can go directly to D. Back edges we talked about earlier, and then cross edges are associated with something that is neither a descendant nor an ancestor. So if there's a relationship there, it's considered a cross edge because you're not actually going to be hitting it when you're following the traditional tree. So in this particular graph, for those that can see it well, sorry, that's a little dotted. What are the two forward edges? Let's start there. So these are edges that lead from a node to a non-child descendant. So it's kind of jumping more than one.
What is it,
AF would be one, yes, right here.
Is that
HG.
EG would be the other one, yes. So what about the two back edges?
Well, that'd be D to A, right?
DA would be one, yes. And FB, exactly. And what are the two cross edges? HG is one of them, yes. DH. Exactly. Yeah.
So every directed graph can be represented by an undirected graph, right? And
well,
let me rephrase
okay.
that. A directed graph is an undirected graph with an additional layer of more information.
Correct. I mean, you can consider an undirected graph to be a directed graph, but it's pointing in both directions.
Right.
So if you try to represent a directed graph as an undirected graph, you will find loss in your data.
Right. So that's what I'm thinking about it too. In the
Yes.
sense that you can, so like an undirected graph is going to show a certain amount of information in a relationship between nodes, and a directed graph is going to provide yet additional layer of information between graphs.
Yes.
Which, and then even further, an undirected graph is not quite the same as a directed graph with all bidirectional connections.
Right.
Since technically that would be still a layer further of information than undirected graph.
Correct. So, going back to our original analogy, the internet, is it directed or undirected? Yeah, I mean, just because you have a hyperlink going from Joe Blow's blog to New York Times doesn't mean that the New York Times is a hyperlink to Joe Blow's blog. So yes.
I have a question.
What's up?
Why is
Should I
getting
go back?
to F a forward?
Oh, yes. So this graph is a little bit deceitful. So as you're traversing, when you hit A, you're going to go first to B before you end up going to F, which will then go to E and then go to F. So you've already hit F before you end up going back up and checking the next thing with A. So when you're evaluating this particular arrow, that particular edge, you are not actually going to end up following it.
Yeah, you've already been in.
Exactly.
If we reverse implementation the way we do our depth first search,
Right.
I mean F would still be if we're a forward edge, but so C here is also
Well, you can never, when you go to B, you never end up actually getting over to C, because C traverse down, but you'll end up at G.
Is there a way to change the way we traverse this tree such that? Okay, never mind.
Yeah, and we will be talking
Yeah.
about other ways of traversing trees. We'll be doing more talking about like breadth first search. You can also kind of define your own way if you have particular heuristics that you want to be hitting. Starting there. Yeah.
Sorry. For our examples, I'm assuming we're using the lower value first in terms if we're comparing the letters. if we were to do it in the order B, C, and then F, starting from A, we check B first, and then we go through as far as it goes, then you
Yes.
try C. Okay.
Then you'll pop all the way back up to A, and you'll
Okay.
check C.
Okay.
Yes, correct.
Understood.
Yeah, thank you. Any other questions? Yeah.
Are these searches happening at the same time, like A to B and A to C?
So they are happening on the stack, which means, I mean, the best way to think about it is no. They're not happening at the same time. First, you're going from A, then checking B, then you're going to handle everything that B does before you end up going back to A and checking C. So you start with A, go over to B, go over to E, go over to G, or sorry, go over to F, go over to G. That's the way I go. And then you hop all the way up when you get to G, hop all the way back up to A, go over to C, and actually go over E and then H first, but yeah.
Is there a reason that we don't go to F because we've already gone to F?
Yes. So you don't want to go from A to F because F has already been visited, and that would be going back to our labyrinth analogy, kind of checking all points again.
This is like an exploration function.
Exactly.
We're prioritizing not hitting C node twice.
Exactly. Any other questions? Cool. So simplicity. We consider a cycle to be in a directed graph to be some circular path where you start at some node V0, go through a bunch of other nodes, and end up back at V0. So cycle, circle, different ways to think about it. So for example, if you start at B and you go to E, go to F, go back to B, that's a cycle. You can go around there forever. It's like putting a circle in this labyrinth, which is once again why you want to be marking all the spaces that you visited so that you can actually be continuing to move forward and not just wandering randomly. So a graph without any cycles is called acyclic, and you can test for acyclicity very easily. If it has no back edges, there's not going to be any cycles, because that means that it never tried to avoid any edges. So very simply, that will mean that there's no cycles. So that's also linear time, which is really nice. So a directed acyclic graph is actually something that we use all the time. For example, when you're trying to figure out what you're going to do today, you might wake up and go to the lab and work on FDF. If you finish it, then you can work on fractal. But let's say you don't want to do that, so you do D first, work on printf, then you can do push swap, but not beforehand. You can break this down as a directed acyclic graph where there's no actual circles that go back. But we actually use these all the time in how we plan out and plot out our days. So if you were to make this into a to-do list, or actually the other thing is, you can't start working on FDF until you go to the lab. So you can think about it as a lot of like causalities. Like you can't just do it from your dorm room. No one does that ever. And you of course can't go to the lab if you're not awake properly. Depends on the day. Depends on if there's an exam. So if we were to actually write out a plan for us for the day, that would actually be a linearization. So it compiles it down, compiles is probably the wrong word in this context, to one set of things that you could be doing. But these things could be different. So for example, you can do A, then B, then C, D, E, then F, G, H. Or you can do A, then B, then jump over to E, then do C. Because these aren't the same tier, you can be working on any of these in any order. And yeah, so there's multiple linearizations. So a couple properties of these DAGs. So in a DAG, every edge leads to a vertex with a lower post number. So we're going to start bringing back the idea of pre and post numbers. So as you continue to go down, so if you, when you wake up, you're not, let's say when you go to the lab, you start working on FDF, then you go work on fractal. When you go back up to work on FDF, you're going to leave that node, so have a post number before you can go back to B. So B's post number is always going to be higher than C's, because C will have already completed before you could have completed B. Doesn't lend itself great to this example, but we'll keep playing with it. Also, we have these notions of sources and sinks. So a source is basically the starting point for any DAG, and a sink is basically an ending point where you've gotten to the end and you can't go anywhere else. So for every DAG, there's at least one source and one sink. You have to start somewhere where there's no edges coming into it, and you have to end somewhere where there's no edges going away from it. So like, yeah. So I guess I kind of answered this question for you. What are the sources and sinks of the above example? Does that make sense? The source is the wake up, and working on these guys are the sinks. Cool? So strongly connected components. So we're going to define connectedness a little bit differently in a directed graph. Basically, well, it's actually the same definition, but a little bit different because of the directedness. So a graph G is connected if with the two F's means if and only if. So graph G is connected if and only if for any two nodes, U and V, there's a path from U to V and from V to U. When you're in an undirected graph, you get that as for free, because if you can get to one, you can get back to the other. But here, for example, if you're starting at A, you can get to K, but K can't get back up to A. No way. So while, so of course, cyclicity is going to be harder to find in a directed graph because of this property. But there is another notion that we can start grappling with, which is this idea of strongly connected components. So if we break up this directed graph into different pieces, we can see that some pieces are connected. So if you start at G here, you can get over to K and then back over to G. So for this little piece of a graph, it's connected. So we can actually think of the graph overall at the meta graph, which is actually the term, as this graph here, where if you're starting at A, you can be ending up down here. And that would be kind of a way for the information to flow. Yes?
Yeah, sweet.
All over everything math related I wrote that in my life. And it seems to mean something different than
Yeah.
every single math thing I've seen in my life.
Yeah, of course.
Yeah, of course. Math. But they also seem to have like some elements that like kind of make sense as a whole.
Right.
So like, would you happen to have a in-scope way of explaining like more fundamentally what the difference between strongly and weakly is, as long as it's in-scope?
I can tell you what a strongly connected component is.
That's a good fucking start.
Yeah, so strongly is just a qualifier generally for anything in math. Or strong, strongly, same with weak and weakly. So what the purpose of it is not to be rigorously defined as a vocabulary word. The point is to alter some other defined word to make it seem more important or influential. So this is it's more than just a connected component. It's strongly connected, meaning from any node you can get to any other node. So it's more than a connected component, and that's really all it's supposed to mean. And then for individual uses, you're going to have to figure out what it means in that context.
So it's like this arbitrary thing has more properties than without the word strong. And
Yes, or
conversely,
more strict properties.
more strict properties. And conversely, weakly would be this has fewer properties or looser properties.
Yes.
Then okay, cool. That's really okay. Thank you.
So if disjoint sets of V are a member of set G are connected, is that the correct way to read that?
Here.
Yeah.
So disjoint sets of vertices within G are connected.
Okay,
Yes.
so that symbol is within.
Yes, sorry. Yeah, I'll keep trying to throw math terminology there. vertices within G. And once again, I sprinkle them in there so that when you see them outside of here, it might be a little bit less scary, hopefully.
Yeah, that's helpful.
So what's cool is that when we look at a directed graph, so these are cycles in here. You have to have a cycle if you're going to get from one point all the way back to the same point. So to get from G to K, you have to have a cycle going from K to G. So this is not a directed or a DAG, a directed acyclic graph. It is just a directed graph. But when we group up all of these strongly connected components, it actually becomes a DAG, a directly acyclic. A directed acyclic graph, which might be more interesting in terms of looking at the meta properties of this. So, for example, and you might have heard this one again, for the internet, there might be a whole bunch of sites that frequently link to each other, like Facebook to Twitter to LinkedIn. I don't know. Where's a bunch of people that things link to each other? Reddit to everywhere.
Would it be appropriate to say, like, pages within the same domain?
Pages within the same domain might be a good way of thinking about it. So those are likely all going to be connected to one another. So if a lot of websites look into that, it could be a sink for the entire system. So for example, if you go to Facebook, Facebook never wants to leave Facebook. So it's going to keep looping back onto its own domains. But if you're coming from outside of Facebook, so it would be effectively a sink, even though you're still moving within that one system. So for example, like looking at our example again, if you start at Joe Blow's blog, and then it takes you to, I don't know, Twitter, and then Twitter takes you to Facebook, Facebook's going to try to keep you here forever as a sink. And Joe Blow's blog, no one links back to it, so it's just a source. Yeah?
Fun fact, Wikipedia is a sink on philosophy on its own page. If
Does
you
it-
play Wikipedia, Spelunking, as they call it, is if you click the first blue non-italicized link, which is a hyperlink, you'll end up at philosophy no matter what you do, from no matter what page.
There you go. So an example of a sink. So when we consider this meta graph, we can identify useful properties of it. So what would be really nice is if we could not only figure out all this structure, but also come up with the individual strongly connected components. That'd be really useful to do for some huge graph. So it'd also be really nice if we do it quickly, and it turns out we can actually do this in linear time. It'll be a little bit slower than other methods, but by the factor of a multiplicative, so not that much. So it'd be really nice if we could decompose some directed graph into its strongly connected components and show all the relationships between them. So yeah, once again, thinking of the internet, it'd be really useful if we know which components are connected strongly with one another, and which are just shooting into them or shooting out of them. So yeah, using a similar depth first search, we can find this algorithm. So to do this, we'll start with sync and work backwards. So this raises two questions. So basically, another way to think about this is, if you're in this sync, you know you're in this sync, and you can't get out of it no matter how far you go. So you can check all of the nodes in here, and know that you can't get out. So if you could kind of start at the sync and then move out to each individual connected component before it, you could kind of re-traverse this graph. So first we have to know if we're in a sync, so we have to identify where the most sync-ish place is, the biggest sink, the kitchen sink. And then after we identify that sync, we have to have some way of figuring out what we should be doing next. So it turns out that we're going to use this post numbering again to identify all the information that we need. So let's jump into how that's going to look. It's a little complex, but we can do it. We can do it. So finding a source is pretty easy. As we were talking about before, the node with the highest post number is the source. So for example, if you start at A, actually this is reverse, so we're gonna go back here. So if you start at A, you're gonna do its pre-visit, and then you're gonna have to go through basically everything else in here before you finally go back up the recursive tree and do the post-visit of A to check and see if there's anything else. So you do its pre-visit, it looks at B, B does all of these other things, goes down through all the different branches of this paragraph, and eventually you come back and you check A again, you see there's no other nodes that it's pointing to other than B, and then you do its post-visit. So A has the highest post-visit for any of the nodes in the tree, or in the graph. So if that's a nice way to do a if that's a nice way to find a source, how would we find a sink? Well, one naive way to do it, and one good way to do it, ultimately, is if we reverse the graph and just start looking at every single directed edge to be looking the other way, we can then find the source again, and then it is it ends up being a sink for the original graph. So now, if we look at the highest post number of the graph's reverse, it will give us the sink for the original graph that we're looking for. Cool? So now we've identified a sink. We can look in that sink, find all the stuff within it, and then how do we go from there? Like, what do we do next? So if we've already found all of these highest numbers for the reverse of the graph, then we conceptualize removing all of the numbers that are associated in here. Then all we have left are these couple connected components. So we want to find the new sink out of those new connected components, or out of those remaining nodes. So if we can find another connected component out of just these four, that would kind of be the next one that we want to grab and record the information of to identify where the next connected component is. Luckily, we've already, and basically we're going to want to do this the exact same way as we did the first one. So we grab the next highest remaining post number from the reverse of the graph to identify it, and then go forward with that. A little hard to wrap your mind around, I know, but basically you iterate. So this should be put up. But yeah, so first, like really looking at the algorithm overall, what we're going to do, we're first going to run depth first search on the reverse of the graph, grab all those numbers, and then run the undirected, or run the same algorithm that we used to find these connected components on the graph. And then basically do it for the next one and the next one and the next one. So breaking this down to an actual concrete example, this one, when we run this graph backwards and find the post numbers, so we run it backwards, we find a particular ordering. So we find that, if anybody can't see that, this is too low, I'm sorry. We have some order of numbers. So then so we're going to start with G, and we're going to look at all of the different components associated with it. Okay, we see it's G, H, I, J, K, and L. Now scrap them all from this first list, and just look at the next highest post ordering number associated with that original depth first search. So now we're going to have to get D. D, we try to go to any other, once again, look for that connected component. We see that's connected to nothing, so we just let it be out by itself. Then we're going to do the same thing going forward. And that's a little abstract. What's your question?
So we're trying to search through a tree, right? And in order to do that, we're gonna need to reverse all of the links. How are we gonna reverse all of the links, like implementation wise?
So
Is that easy to do?
it is linear to do.
Okay.
So actually, that's one of the homework questions. I actually don't think I put it on the homework sheet, but I can point you to where it asks for that in the book.
Gotcha.
And that's actually one thing that you could be thinking about. which is how do you reverse a directed graph?
Yeah.
And you can think about it very similarly to how you would reverse a linked list in terms of implementation.
If you store the directed, well, the directed graph as a adjacency matrix, you could reverse it. That's
An adjacency matrix might even be an easier way. But the way that we've been kind of navigating through these lends itself a little bit more to an adjacency list. But yeah, that's a good point. So if you, what is it? What's the term where you flip it?
roted column. I'm not sure what the is it transpose?
Inverse?
I think
No, it's not inverse. I think it's transpose. Yeah.
Yeah.
Transpose sounds
all
right.
the rows, columns.
So yeah, that's
Yeah, you
that's
should
whatever
flip
that
it.
is.
Yeah. At least think about it as flip it over the symmetrical line that is the diagonal of the matrix. And that would flip it effectively. Yes?
If you kept track of every single node and its connection to others as a relation database row, you could just multiply by -1.
Yes, probably. I don't know if that would be the most efficient way to store or access that data though. So any other questions? I know it's a little bit abstract. I recommend maybe coming back and looking at this a little bit more to kind of see how everything plays out. Some of the homework that I've assigned actually will dive into a little bit more. So what is time complexity? It ends up actually still being ON, mostly because the depth first search is ON, and this connected components algorithm that we played with earlier, that I'm playing with now, is also ON. So awesome. I mean, it'll be a couple of yes, but luckily we can throw out the two and just call it ON. So that's actually all we have today. It's a little bit shorter of a class. Yeah, a little under an hour. So some potential homework, if you're so inclined. Did anybody do any of the homework that I assigned last week? Yeah. So Mr. M. Hurd actually was the only one that submitted. So basically, for those that weren't here last week, I challenged what's the term?
Code golf.
Code golf, yes. So for a merge sort, I tried to have people do code golf, which is basically try to use as few characters as possible to do something. So I'll talk about this and then actually show you his result that he sent me. So if you're interested in thinking about depth first search more, which is a very useful tool, this is actually, if you think about it, if you think about your approaching fillet, if you're working on fillet, you're actually doing depth first search as you try to place all of these different nodes, or place all the different pieces. What you're trying to do is go down a whole bunch of different branches of a tree. So yeah, look at the first couple problems from the book. If you want to see how this actually plays into real life problems, and like this will be actually very useful if you're thinking about problems that you might see on an interview or something like that, where it's in actual words and like concept as opposed to just mathiness. Look at these few problems, 3.8, 3.15, and 3.16. And if you are interested in, if anybody's heard of the Königsberg bridge problem, so it's a traditional graph theory problem. It has a pretty good Wikipedia page. That's 3.26 is just doing that problem. So it might be interesting to look at their information on that. If you're more into coding stuff and actually building things, try to actually implement an adjacency matrix and an adjacency list. And then if you could actually start building some functions to add vertices and add edges and perform depth first search, I promise you that that will be one, useful for interview prep, and two, probably useful in the problems that you're going to see upstairs. Because these data structures, like linked lists, are relatively fundamental and can be applied to a wide swath of problems. So yeah, that's all I got for you. I can show you guys Matt's code golf. I wish you were here to show it off himself.
Did you run it?
Huh?
Did you run it?
I did not run it, no. I trusted him. Do I still have it?
You trusted Matter.
So
He tried to fish you, right?
he succeeded to fish me. So this is his merge sort. as you can see, it's really easy to understand.
EE. I know exactly what EE does.
So it's trying to minimize the amount of characters that you use. So yeah,
Wait. Did he use spaces or tabs? Because even if
use tabs.
okay, good.
Are we talking unique characters, or are we talking like if I use the same character twice? Does that count as one
Total
character?
number.
That's two characters.
Wait,
Unique
So
characters.
that is, are you just because you got unique characters, I could put everything in an array.
I don't know if that'd be most useful.
No, putting it all in an array is less efficient because you have to use the brackets with index.
I think. Oh yeah, I also required it to be normable. So like you have to fit norms. You can't just do a whole bunch of macros and that BS.
Well,
A copy of this is actually online as well. The author has a free version that is in the base camp. So for those, yes.
norm, you can't have variables that are just single character.
I am not looking at that rule.
Also,
Well,
can we
unless it's like for the
pointer something at the wrong place? I hate that.
Well, we don't have any code golf challenges.
It
I hope
There are required in our
I'd love to see some more submissions. If anybody else is not officially a part of the Slack or the base camp and would like to be, feel free to message me, C Summers on Slack, and I can add you to those things. But I think most people here are. So yeah, thank you everybody for coming.